Whenever we
Yeah.
feel like when there is no left, then we consider this value, right? Correct na?
Yes.
So we consider 2. Now we look for if there is any right, right? It doesn't have any right, so that we went on to its parent. Correct?
Yeah.
So we went on to its parent, which is 4. So now you are done with you taken the parent. After taking the parent, now we will see does it have any right or not. Yes, it has right, so that we went for right. Correct?
Yes.
So let's analyze one more time. So this is what we did now. So as part of depth first search, we just directly getting into the left part. So we just getting into the left part. Perfect. So once we are done with left, it means this is how it looks like. So I'm just directly traversing to the left. So once I am done with the left, I feel like there is no left here. After 2 there is no left, so that I take the latest value, so which is been added to that result, because I captured the current left. So as part of left, you are also actually capturing the root also, because whatever left you are traversing, right, which also act as a root. Correct na? Yes or nobody?
Yes. Yeah.
Then it means you are done with left hand root, so it's time for us to move on to the right. So you just move on to the right. Now when you move on to the right, you know that there is no value on the right for this node. So it means it doesn't have left and right, so you took the 2 already. Then take the next root, next root, which is 4, right? So which is the immediate parent of the previous value. So you take that root. Now it means indirectly you are traversing this one, and you are also traversing left of this 4, so which is already done. Now it's time for us to move on to the right. So when you move on to the right, so I see that there is a value 1. There is a value 1. So that what we do, so we will again keep the right. Again we apply the, if we went on to the right, and if there are any left to it, so we will just add to it until we find the current left is null. So I just added 1 to the stack. Now there are no left here, so that they pop the 1 from the stack, add here, move on to the right. There is no right, so that obviously you are done with left and right for this root 1. Now it's time for us to move on to the root parent. So if you closely see, this part is completely is a left to this root, so which is already present on the stack. Take that root and add here. Now you are done with the left part. Now it's move on to the right. So when you are moving on to the right, so this is how it should be. So let me take 4 7 6, something like this, so it would be helpful. So now your time, it's time for us to move on to the right part. So when you are moving on to the right part, same process. Then same process, right is 3, then take it, so left, complete left, so which is 4. So you took the 4. 4 doesn't have left and right, so you are done with the 4. Now its immediate parent is 3. Took 3, and 3 3 left is done. Now it's time for us to move on to the right. So the right is 7, so that this is right, so right is 7. So again load those right to left into the stack. So you just take that 6, because it doesn't have left and right, so there is no traversal. Then you will have immediate parent as 7, so take that 7. If you want to explore right, there is no right, so that you are done with in order traversal. Clear, right, Ajay?
Yes.
So how do you write the logic here? If you want to come up with a pseudo code, how do you write the logic?
So first we have the root node 5,
Yeah,
right?
yeah.
Consider like that's a current node. Then we will keep going till the extreme left
Yeah. So what do
until
you do
the
when you
current
are
is
going
null.
extreme left? What do you do?
Stack dot push current,
Yeah,
then
because we
current
need to
equals
try and
root
take.
of left.
Yeah, that's it. So what we do? So this is what we did, right? We initialized current as 5, so that we just went to extreme left and adding all the left
Yeah,
to the stack. Then when we
correct.
find we don't have any left, then we just pop the value from the stack,
All
then
from the
add
stack.
it to the
Yeah.
result. Now this is current, right? Now when you pop from the stack, current is going to be 2, right? So now you just write current equal current dot right. So it means you need to explore right part, but there is no right here, so that again current becomes null. In the next iteration, next top element will be popped, which is 4. Now current is 4 now. So once current is 4, current equal current dot write. So current write is 1. So that current becomes 1. Now it's time for us to load current values into the stack. Done. So there is no left. Then simply you take 1. So repeat the same process. Correct?
Yeah,
So what is the time complexity?
I think order of n.
Yeah, so you are simply visiting all the nodes, right? So what is the space complexity?
I think same.
Yeah, order of n. So we are using into the list.
Yeah.
Yeah, so simple tree node current, which is root, and a stack of tree nodes. And list of integers, array list, and as long as current not null or stack is not empty, either of the case we should move on, right? Should not be end, right? Correct?
Yeah.
So while current not null, just add current to the stack, then just move on to the left. Once it is done, so you are into the last left will be on current stack. So that take that value from the take that node from the stack and add this value to the list. Then you are done with it. It internally covers left and root, so that it's time for us to move on to the right. Correct? Clear, Ajay?
Yeah.
So return list. Yeah, so that's how it works. Okay, done. So now the beauty of inordered traversal is, so let's talk about the concept of binary search tree. Okay, so binary search tree. So binary search tree means, for example, if you take a root, all the left nodes will be less than or equal to the root. So less than the root, not equal. All the left nodes will be less than the root. All the right nodes will be greater than the root. So it applies recursively. Understood? So if this is the root,
Yes.
then less than root and greater than root. So it applies all the nodes recursively. Let's say I will take a binary tree, binary search tree. So something like this. Okay, so let's take this is the tree. So if you pick up this is the root, let's say this is the root, and all the values left side or less than 5, right?
Yes.
And all the values on the right side greater than 5. Now if you pick up this one, so all the values less than left side less than 4, there is no right. When you come to here, all the values left side is less than immediate root, and all the values right side is greater than immediate root, right? So it means if it is greater than this one, means it is greater than its parent also. So this is binary search tree. Okay, so the beauty of binary search tree is, in a binary search tree, if you apply inordered traversal, you always get a sorted array. Can you tell me what is the inordered traversal here? So we
It
traverse
will
from
be
here
1, 2, 3,
to
4,
3.
5.
So first we'll come here, right? So 1, then
Yeah.
root, then right, then left, then root, then right. So when you go right, so you'll come here,
6,
then root,
7, 8. Yeah.
and right. So if you clearly see, so the in-order traversal, right? So in-order traversal in a binary search tree will always give in sorted order. Okay, so this is the thumb rule. So let's, based on this concept, we can solve couple of problems. So let's look at before getting into here. Yeah. So we want to search an element in a binary search tree. So how can we do that? Let's say this is your binary search tree. So 4 2 4 2 7 and 1 and 3. Okay, so he has given value equal to, so you just need to return true. For example, value is equal to 0, then in this case it is false, but here it is true.
So now can you see your screen? Let me in the lead code window.
Yeah.
Yeah.
Right, so this is what, right? So if the value is 2, 2 is available in tree, so it will return true. If the value is 0, then it will return false. So how do you solve it? And it is a binary search tree. So they already given it is a binary search tree.
I mean, whatever the value searching for, if it is less than the root node, we will go left.
Mm.
If it is greater than, we'll go right.
Yeah. Correct, na? So, if it is
Yeah.
not binary search tree, how do you find out? If it is not binary search tree, how do you find out?
Then I think we have to do a normal the traversal that what we are doing and
Yeah.
keep comparing.
So you can do in order or what else?
Pre-order. Yeah.
Pre-order. So
Pre-order.
these are the two orders we discussed, right? So we visit all the nodes. Whenever you find a value, you return true. But in this case, the time complexity is linear. So, but here it is a BST, right? So it's a binary search tree, and we know that root on the left side you have less than value, less than root dot value. On the right side you will have greater than root dot value, right? So we know that it's a binary search property. So let's apply binary search concept on here. So let's say this is your tree. So let's identify value 0 is present or not. Let's say value 0 is present or not. So how do you do that? First you get into here. Here current root value is 4, which is which is greater than expected root, right? Then where should I move? Current value is 4, which is greater than expected value 0, because we want to search 0 is present in this tree or not. So when I start from root, the root value is 4, which is greater than the expected value. Then where should I go now?
If the current value is less than the root value, then go left.
Yeah. So I should go left, because if I go right, there is no use now. On the right side, you always have a greater values compared to the root. Now I come here. In the current value 2, which is again greater than expected value, then where should I go?
Left.
Again I come left. So similarly, if current value is 1, which is again greater than expected value, where should I go? Left. But left is null, right? So left is null. So as left is null, definitely you can return false. Correct? So similarly, if the value is equal 3, then how we should go? This is the same structure, right? If the value is 3, now first you come up with the root 4. So which is 4 is greater than 3, so that I should go to the left. So when I go to the left, 2, so 2 is less than 3, so that I should go to the right. When I go to the right, so I found a value 3, which is equal to 3, so that I can return true. Correct? So what is the time complexity here?
Time complexity of the search. At the worst case, it can cover, I think, all the nodes.
Yeah, it's going to be linear, right? So something like this you have 1, 0, minus 1, minus 2 and on. You just get into that route. But what is the best case? If the tree is
We can
balanced,
get
if
rid
the
of
tree
it
is
from.
not balanced, then it is n, or big O of
Mm.
h. If the tree is not balanced, you can say big O of h rather n. If the tree is not balanced, if the tree is balanced, so it is going to be log n, correct? At every step you are
So
eliminating
if the
n.
balanced or not balanced, does that mean it's shorted, like it's a BST tree or not BST tree?
It doesn't matter. So balanced means every node will have two nodes.
Two, okay.
So something like this. If the current level is filled, then only it move on to the next level. So this
Okay.
is level 2, this is level 3, this is level 4, right? Then only it will get into level 5. Okay, so if the current level is, this is called balanced binary, balanced tree. So if the tree is not balanced, you get into the complete height of the tree. If the tree is balanced, then it is going to be log n, because when you go left, you are eliminating right? Yes or nobody?
Mm.
So if you go left, definitely you are, if you go left, if you choose left, you are eliminating right. Again, if you choose left, you are eliminating this right. So each time you are trying to eliminate n by 2 elements, right? So n by 2, n by 4, n by 8, and so on, so that it is going to be log n. Correct?
Understood. Yeah.
So, yeah, how do you write a recursive code for to this DFS?
Recursive one, like we'll start with the root node. If the current element is less than the root, then current will move to current will be current dot left.
So you are giving recursive code or iterative approach?
Recursive.
Yeah. So simple, right? So yeah. So this is my DFS of root. So if root is null or root dot value is equal to value, so you will just return root. Otherwise, we will compare. We take a decision to go on left or right. Right. So let me
Mm.
quickly write. So in case if root is null or root dot value which is equal to value, then it's time for us to return root. Otherwise, so if root dot value greater than value, then return search vs
Same.
root dot left comma value, else right comma value. So in this case, we are expecting the root node, so that's it. How do you write it as a iterative approach?
Iterative approach. Like we don't need to call the same method again and again. What we can do is the root we can keep it in the current, and yeah, the first condition will still correct. Only the second row line will change.
Yeah, that we can avoid. So some ways, okay. So current equal root. Then what should be the
Root.
condition? While condition?
While condition is if value is less than the root dot.
No,
Sorry,
no,
if value is less than current dot val.
no. You should repeat this, right? Keep on till some point in time. So
Yeah,
what is the
while
time
current
interval?
is not equal to null.
Then is this enough?
And current value is
As
and
long
current
as
dot value is not equal to that value.
yeah. Then current equal. What is going to be current?
Then current going to be no. Then we have to check, right? If the value is less, then we have to go to left. If it is greater, then we have to go to right.
Does it work out?
Yeah. Current equal to current dot value greater than.
Clear?
Wait, let me check. The current value is greater than to val. Yes, we're going left. If not, then we're going to right. Correct.
That's it. Okay, so let's look at other problem. Okay, so you were given a sorted array. We should convert this sorted array into balanced binary search tree. So what do you mean by balanced binary search tree, right? So let's move on. So you are given a sorted array. So let's say the array is something like this. Let's say array is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So this is a sorted array. One way is you can create a binary search tree something like this, right? So 1, 2, 3, 4, 5, 6, and so on, right? Clear? So
Yeah.
and so on 10. But this is not balanced binary search tree. So what do you mean by balanced tree? So balanced tree means only last two levels may not be filled. All the levels should be filled. So it means once the current level is filled, then you can move on to the next level. Okay. So at any point in time in a balanced binary search tree, only last two levels won't be completely filled. For example, in this case, if you see, these are the only two levels which won't be filled, right? Yes or nobody? Completely? Only last level won't be filled completely. So what do you mean by balanced binary tree means once the current level is filled, we can move on to the next level. So without filling this current level, right? If you write something like this is invalid. Understood?
Got it.
Okay, so once the current level is filled, we should move on to the next level. Now that's how we should do that. So always the height of a balanced binary search tree is going to be big O of log n. So if there are 8 elements, height will be 3. If there are 16 elements, height will be 4. 32 elements, height will be 5. Okay, so that's how it is. Just a second. Hello. Yeah. Yeah, వచ్చా no problem. ఓకే ఓకే ఆల్రెడీ లోపలికి వచ్చేసారా ఓకే 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 నో ప్రాబ్లం
Daddy, Daddy, we go upload full card, Daddy.
క్లాస్ చెప్తున్నా
Daddy, upload card.
క్లాస్ చెప్తున్నాను
Come on, in the car.
సో
In the car, people space.
సో హౌ డూ యూ సాల్వ్ ఇట్
In chala people
so we need to invert the in-order traversal so that you can get a balanced binary search tree.
Invert in the sense.
So let's say if we want to convert this into in-order traversal, so how many elements we have total? 10 elements, right? So definitely you have 1, 2, 3, 4. Let's say if I want to do this as in a traversal, so this is going to be the mid element, right? So if you see, let's remove this 9, 10 just for our convenience sake, and this is going to be middle element, and you have left and right, correct na? Yes or no?
Yeah. Yeah.
This one, then left you have how many? 4 elements. Then you have right. So left you have 4 elements. Right also you have 4 elements. Okay. So let's see. Let me do that. So 1, 2. So definitely it is 1, 2. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So do you think it's a in-order traversal? So if you closely see, does it look like a in-order traversal? Is it a
Yes.
is it a binary search tree now?
6, 7, 8, 9. Yeah.
It's a binary search tree, right? So what I did, if you closely
Yeah.
see, this is what I did, right? You have this and this and here and here, right? So 1, 2, 3, 4, 5. Then again I completely go on to the left side. 6,
Mm.
7, 8, 9. Right? It's simply in order traversal, right? So I was able to construct a tree with in order traversal. Okay, in a balanced binary search tree, last two levels won't be filled again. Okay, so this is last level, this is before last level, right? Let's say this is L4 and this is L3. So except last two levels, all the levels will be filled. If you take a
But
larger input,
if you see node 2, right, that one also half filled.
that's
4
what
is
I'm
also
saying.
not filled, right?
These are last two levels, right? This one and
Oh,
this
right.
one.
7. Mm.
These two are last two levels, so which won't be filled anymore. All other levels will be filled. If you take a larger input, then you can understand better. Now I want to invert
Okay.
this concept, right? How do you invert this concept? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So one thing for sure, this should be in the middle, right? Yes or no?
Mm.
This should be the root, right? Because if you want to maintain balanced binary search tree, then you should make sure that the middle element is going to be the root. Okay, so 0, 1.
Mm.
So let's go on to that. So let's say these are the indexes. Let me take it as a 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay. Okay. So you have indexes 0, 1, 2, 3, 4, 5, 6, 7, 8. So left is 0, right is 8. So he has given a sorted array. We will find out a mid. So what is the mid? 4, right? 4 is holding
Yeah.
value. Now what is going to be the left? This is going to be
14.
the left, right? These
Yeah.
all elements come under the left. It means 0 to 3 come under left. And these are going to the right, correct? Index 5 to
Yes.
7 going to the right. Correct? Again apply the same concept here. So find out a mid. 0 to 3
Mm.
mid means definitely you will get this, correct? Correct
Yes.
number. So you will get 12. Then again you will have left. So left is going to be 0 to 0 and right is going to be 2 to 3. Correct? Yes or no?
Mm.
So this is going to
Yes.
be left. This is going to this is going to be the right. This is going to be the left. So 0 0 means definitely you will have only one thing. So there is nothing you can do. And 2 3. So once you go to right, these are the 2 3. Correct nobody? Yes or no?
Yes.
So 2 3. So 2 plus 3 by 2 means again you will get a mid as 2. So definitely this is my mid. Now when you go left, so definitely mid is going to be uh, there is no left, right? So when it comes to here, so there is no left, so you don't need to worry about it. Hope you are able to follow me now, Ajay.
Yeah, I got the word concept. Like we need to
Yeah.
find the middle, then go left, right.
Yeah, so when you go to the right, so it is going to be the right mid plus 1 comma right, so which is going to be 3 comma 3. Okay, so 3 comma 3, so
Which is
definitely
14.
you will get 14. So similarly, if you come 5 to 7, then 13 by 2 means definitely you will get 17 here. Then 16 here you will get, because 5 comma 5 is going to be left, 7 comma 8 is going to be the right. So definitely 7, so 8. Then right is going to be 8 comma 8, then which is going to be 19. Okay, so
Mm.
somewhat it is more or like similar to this only. Somehow you see last two levels won't be filled, all other levels will be filled.
Mm.
Understood? So what is the time complexity here to construct a binary search tree here through sorted array?
And login.
Is it n logging? What are you doing here?
We're
Why are
finding
you
the middle,
confusing?
then
Are we sorting
traverse.
anything?
I think time is order of n only.
Yeah, because we are just we are just visiting every element and concerting a
Yeah.
BST, right? What is the
Yeah.
space complexity?
Yes.
So for stack, if you
Same
go
order.
with if you go with recursion, so for the stack frame, it is going to be big O of h, right? Correct.
Hmm. Yeah.
And for completing constructing tree, which is going to be big O of n, right?
Hmm.
Just a minute, Ajay.
Sure.
So how do you write a logic to this, Ajay?
Sure.
How do you
Logic
write a
basically
logic
you
to
can
this?
find the middle element, then go left, right,
Yeah.
recursively.
Yeah, so this is what we did, right? So 11, 12, 13, 14, 15, 16, 17, 18, and 19. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So let me note down. So the mid is going to be index 4, right? Right. So index 4 is going to be the mid. Then you will traverse the left and right, correct? So left is going to
Yes.
be index 0 to 3 is the left, right is going to be mid plus 1. So 5 to last index, 5 to 8, correct? Now
Yes.
0 to 3 mid is going to be what? Index 1, correct? 0 plus 3 by 2, index 1. So left is going to be 0, 0, right is going to be 2, 2, 3, correct? Clear, buddy?
Yes.
Now again, when left and right are same, so you will just consider that. So index 0. Now if you come here, 2 to 3, mid is 2, so that here you will get 2, and left is going to be uh, what, buddy? You will just 2 to index minus 1, so it becomes 2 comma 1. That's what it happens, right? Yes or no,
Hmm.
buddy? Initially here left
Yeah.
is 0 to 8, you find a mid, then 0 to 3 you went left, and 5 to 8 you went right. So here also, here 2 to 3 means left is 2, so 2 to 1, because 2 minus 1, so definitely this is invalid. Then right is going to be 3 to 3, right? 2 plus 1 to this right, correct na?
Which is 14. Yeah, which is index 3.
3. Now you are done with, even if you are done, so now it's time for us here. So 5 plus 8, 13 by 2, so which is going to be 6, so index 6.
6.
Now left is going to be 5 to 5, correct? This is 5.
Yes.
And 6 minus 1, so mid minus 1. Right is going to be mid plus 1 to n, right? So this is 8. Now index 5, obviously here index 5. Now here also 7 plus 8 by 2, 8 means index 7. So left is going to be this one and
6.
mid minus 1. Then right is going to be 8 comma 8, and this is invalid. Then you will get index 8. So if you closely load those values, right? So 11, 12, 13, 14, 15, then 16, 17, 18, and 19. Right? So that's how it works. Perfect. So
So
this,
invalid case comes if the left value is more than right, then that is invalid, right?
yeah, that's it. That's an invalid case, right? So if left is greater than right, so you just need to return null. Otherwise, what you do? So if left equal right, you just return the root. Otherwise, find a mid
Hmm.
and find left and right.
Got the concept.
So let's look that. So definitely you need tree node BST integer array nums integer left integer right. So if left is greater than right, then return null. So you should not do anything. If left is equal to right, then return new tree node of nums of left. Correct now, buddy? Correct?
If both are same, then yes.
You can take anything. Okay, so then now it's time for us to root new tree node. We need to find out mid here. So integer mid is going to be left plus right by 2. So first consider nums of mid, then root dot left is going to be construct BST from nums. It is going to be left to mid minus 1. Correct? Yes or no, buddy?
2 mid minus 1. Yeah, that's right. Yeah, right would be construct BST nums right to
Mid plus 1 to
mid
right.
plus 1 to right. Yeah.
Then finally return root. So now we want to construct a binary search tree for a given nums 0 to nums dot length
Nums dot length minus 1.
That's it. It's very tricky.
It's a tricky one.
Yeah, very tricky. If you are good with recursion, you can easily solve it. Getting that mid thought and manipulating indexes is the tricky part.
And mid thought is also easy, but yeah, last 27 to 30 line number 30th is tricky.
Yeah, this will take care everything.
Yeah.
Yeah. Let's solve. Okay. Yeah, how do you find out? So this in-order traversal, right? In-order traversal is one of the best way to traverse binary search tree, Ajay. So whenever you get a sorted trees or binary search trees, then in-order is the best way to figure out a solution. Because if you go with other things, you cannot figure that out. Okay. So let's say what is saying minimum absolute difference in binary search tree. So you will be given a binary search tree. We need to find out what is the minimum absolute difference. So let's say this is your binary search tree. So actually if we pick up all patterns, right, then solving problems becomes, we will get multiple thoughts. That's why I'm taking off of our problems. Otherwise if we solve all pre-order problems, now our brain will try to pre-order, then in order. So when we club everything, right, then we will get confused. That's why we will take partial problems in all the orders, then we will take up our choice. Few of the problems can be solved with any order, so we can take our choice. Okay, so let's say you have input something like this. It's so the best way to draw the binary search tree is first take all the nodes. Okay, then apply in-order traversal. So 1, 2, 3, 4, 5, 6, 7. Okay, so it's the best way to do that. So let's say I have let's say you have 14 here, then 16 here, 27 here, 15 here, and 12, Yeah, so what is the minimum absolute difference here in a binary search tree? So let's say it is 30. So minimum absolute difference means difference, minimum absolute difference. You can find
I
an
think one.
one, right? So because the
Yeah.
difference between these two is going to be one,
15. Yeah.
right? You may have here you have there are multiple. If you closely see, it is something 1, 12, 30. Is it correct? So this is in one, right? Let's make it 14. Let's make it 13. Okay, so 1, 12, 13, 14, 16, 15, 16, 27. So these all are the elements, right? If you see the minimum absolute difference, you could see difference here is 1, here also 1, even here also 1, right? In other ways, if you pick up any other elements, the minimum absolute difference is greater than 1, so that we can take minimum value which is 1. How do you solve it?
This basically will do traversal, Shinu, and we will somewhere keep the track of the previous node to the current node, and we'll have a global object which will keep track of the difference.
Mm. Okay, forget about binary search tree. Let's say this is not binary search tree. Then how do you find out minimum absolute difference?
Let's do a pre-order traversal.
Okay, so if you do pre-order traversal, what will happen? It becomes 14, 12,
Yeah.
1, 13, right? And then 16, 15, 27, right?
Yeah.
One, two. So root, left, right. So root, left, right. Yeah. So generally you get this. Then what you should do? How do you find out a minimum absolute difference?
So when 14 to 12 we are coming, right? 14 to 12 we are doing, that time the difference is 2.
Mm.
Basically, we keep a maximum minimum value as integer dot max, and if that current difference is minimum,
So what
less
what
than
will
that,
happen if this is the case? If you want to find out a minimum value, what is the time complexity?
order of n.
Can be done with n. Can you find
Because
one
anyways the
with
travel
n?
time is nodes, right?
Let's say if I traverse with this, if you traverse with all these elements, let's say you don't have 13 here, 13 and 15. Can you really find with n? I don't think so, right? Because in this input you are able to do that. You have to compare with every element with other elements, right, to find out a minimum difference, right? In this example it is working, but ideally it won't work now.
Okay.
Correct?
Okay.
Right, so it's going to be n square. So what you should do, once you get an element, you have to sort it. So once you sort it, what will happen? It is going to be 1, 12, 13, 14, 15, 16, then 27, right? Then you can find out a minimum absolute difference by just comparing two elements. Correct? Correct?
Okay, got it. Because it's not a shorted one, so the difference
yeah,
can come between first and last element also.
Yeah. So if it is sorted one, so you can always compare next to two elements, consecutive element, that's it. So you can find out a minimum, because the difference between these two and these two, when you compare to these two, this is always going to be shortest, right? Because it is in increasing order. Correct, Ajay?
Because it's a sorted one.
Yeah, it is sorted one. In the earlier case, you can't tell that. You have to see all possibilities. So in this case, this difference is always shorter than these two element difference, right? These element difference, so that you don't have to compare with other elements. Adjacent elements is always giving optimal result. But in this case, to construct this, first it will take log n, then you have to sort it, then n log n, then getting the minimum element again n. Right? So first you construct with n, then sort it, then find out a minimum element. So which is always going to be the time complexity will be n log n. Now can we avoid that? So it means, what did you understand here? At the end, I need to get a sorted array. Yes or no, buddy? Yes or no, please? But how do you get a sorted array?
If you take a BST,
Yeah, this is BST only, right? Yeah. Let's say you given a BST. Now I want to get a sorted array from this BST. How do I get?
do a in order traversal.
That's it, right? So once you do a in order traversal, so 1, 12, 13, 14, 16, 15,
16,
27.
17,
Yeah.
16,
15,
27.
16, 27, right?
Yeah.
Now you got a sorted array. Now it's time for us to find a minimum value comparing both the elements, right? So this will take linear, and to find a min element again linear, so which is going to be linear, correct? Correct?
Yeah.
So this is
Correct.
for min element finding. Okay, so what is other solution you could think of?
What other solution?
Okay, let's say I don't want to construct this. I don't want to construct this result array. You can solve this now, Ajay.
Yeah, I think that's all good.
Yeah, we already solved
While
it.
doing in order traversal itself, we can compare the root with the next node
Hmm.
and we can do it.
But how do you know that? So when you get into next node, right, you don't have a root now.
I mean, not to the root to next.
Mm.
We can keep track of the previous node. Let's say when I'm coming to node 1,
Mm.
value 1, we know the previous node is 12. That one we can keep track of, right?
Mm. Yeah, so
Then the difference
that's
we
it, right? So
can
when you compare it,
maintain it.
then take the absolute difference, add into the global variable, right? Correct?
Right.
Uh,
Yeah.
Can you solve it in that? That's a DFS approach. Can you solve it?
Yeah.
Okay. Then what
Yeah,
could be
DFS
other
one actually
solution?
can solve it. Yeah.
Yeah. So this is DFS, and we also have a traditional in order. Okay. So can we have other solution? So this is solution one, solution two, and can we have other solution?
DFS is gonna take order of n only, right?
Yeah. This will also take order of n.
Order of n, yeah.
Because you have to look for every possible path.
Yeah. It can be at the beginning also, yeah, maybe. Yeah, we have to do it
So
till the end
what
of
I
the
would
list.
suggest is when you go with DFS, take parent and current, two nodes, rather handling with previous. Okay, so initially
Okay.
parent will be null, then current will be 14. Then when you go further, then parent will be 14, current will be null, 14, 16. That way you will go on, right? So 12, 1,
Yeah.
12, 13. And here also you will get 16, 15, and 16,
16,
16,
27.
yeah, 16, 27. So you can easily find out a difference here. That way you can easily figure out min
Got
difference.
it.
That's an easy way to solve it. Yeah, if you take a global variable, it's not super intuitive, right? So you don't know what is the value
Yeah.
updating and all. Okay.
Right.
So let me tell you one more solution. So this is 14, 12, 16, 1, 13. Right? So what I will do, uh, I will use the concept of tree set. Okay. So
Okay.
of course this is not good time complexity. Other two solutions are giving best time complexity. Uh, so actually, in the initial brute force approach, right? So we constructed tree, then we sorted it, right?
Yes.
Generally, if you so what is the advantage you got after sorting?
The search was quick
Not the search, right?
because
Comparison
we know
becomes
that
quick.
your comparison
Comparison
would be
becomes
quick.
quick, right? So
Yeah.
let's say I have a element something like this. So what is the minimum value? 1, 12, 13, 17.
So one.
Sorry. What is the minimum?
Minimum difference is 1.
Yeah, minimum difference. 1, right? Correct?
Yeah.
1 only. So because now, let's say I have something like this. 1, 12, 15. So what is the minimum difference?
3.
3, right? So how do you know that it is 3? But earlier, let's say if I have a value 10, 12 and 17, so what is the minimum difference?
2.
Right? So what is that? What did you understand here? So what did you understand here? Let's say
So
this
each
is
and
my
every will
current
be
element.
minimum. Yeah.
This is current element.
Yes.
So generally when you are working on, when you are doing what do you say? So when you sort it, when you compare with next elements, this is the technique you are applying, but you are not aware of it. So one best way to find out a solution is you pick up a current element, okay, and find out what is next greater element, right? What is next immediate greater element, correct? Let's say you have 19 also, but immediate greater element is 15, right? Here for 12, yes or nobody?
Yes.
And similarly, in this case also, find out what is immediate smaller element. Here you may have you may have 0 also, but 10 is the immediate smallest element compared to 12, right? Yes or no?
Mm.
So if somehow, if I am able to find out immediate smallest element, immediate largest element, so this is smallest, this is largest, to the current element, okay, so if I am able to find out a minimum difference between these, either these two or these two, I can able to find out optimal answer, right? Yes or nobody? If you closely see,
Yes.
correct na, Ajay?
Yeah.
So 1, 12, 15, immediate smallest element is 1, here the difference is 11, but immediate greatest element is 15, here the difference is 3, but I got optimal answer as 3, so 3 is my answer, right? So similarly, if I have 10, 12, 17, then immediate greatest element here, difference is 5, smallest element is 10, so difference is 2, so 2 is the smallest answer, right? So how do you find out for a given element, how do you find it? So this we call it as successor predecessor. That's all. So immediate greater element, immediate smaller element, successor or predecessor. So we will solve those problems down the line. So the concept of tree set, right? In tree set you have two methods. Okay, so in the tree set you can have a set dot floor of current element, and it will give the immediate greatest element. Okay, immediate element, if it is not found, it will return null, otherwise it will return that value. Similarly, set dot sealing, there is a seal or sealing method. So if you pass the current value, immediate lowest value it will give. So once you have those two values, done nobody. If it is present, it will give, otherwise it will return false. So what is the time complexity you could see here?
It's constant.
Can you think of it? So what we should do, first of all, we keep on add all the elements into the set, correct?
Yeah, already would be order of
Yes,
n.
order of n. Then we need to find out
Yeah.
immediate greater value or immediate smaller value, correct?
Yeah.
To do that, it will take log n, and we have to do
Okay.
it for every element, right?
Yeah.
Correct. So
and
it's
log
going
n.
to be n log n, or you can say n2 log n, because for two times, right? For greater ones, for smaller ones. So it's going to be n log n. Okay. So when it comes to time complexity, it is n log n. What is the space complexity? It's going to be
For
n,
the
right? Because we need to store the elements into the set.
all the elements in the tree set.
Yeah.
Okay.
Of course, this is not a optimal solution, but it's a very good problem to solve through to tree set, so that later in future, if you find a kind of problems, right? You can easily figure that out. Okay, so if it is not a binary search tree, then this is the best solution. As it is binary search tree, you can go with in-order traversal. If it is a normal tree, and if they say that find out a minimum uh, absolute difference, then you should go with tree set, right? Yes or nobody?
Yes. Yes.
So let's say in minimum absolute difference, which is going to be integer dot max value, then what is our job? So we are going to use tree set integers set equal new tree set. Okay, now this is my definitely for traversal, right? You don't have option, no? So you should go with any one of the
Mm.
technique. Okay, so you must go
Yeah.
with any one of the techniques. So what I will do, I want to traverse, right? So let me go with in order or pre-order, whatever it is. So let me choose um, current route. So let me choose in order, okay?
Okay.
Because I need to traverse the complete tree, right? Either you can go with so you don't have any option, so you must do any one of the traverse.
Traverse, we have to do it. Yeah.
So I'll trees are very intuitive, right? They feel how do you feel it, Sanjay? Are you feeling comfortable, or it needs even
Yeah, at least
for
I
me
will to come up with a
also?
recursive approach. Yeah.
For me also, I open trees after a long time, then I also feel same.
Mm.
It's not super intuitive, so you have to think
Yeah.
lot.
Yeah.
So let's say while
I mean, recursive solution is a little easy to come up with, but the iterative one need little brain. Like either it will be stack or queue. We have to see.
yeah, we have to see. Okay, so what I will do, set
Current
equal to
like,
set dot add up
we need to add it. Yeah.
current dot val, and current equal current dot left. Oh, we will add to stack also. Okay, it should be, it is not easy to write line number 27. Okay, so line number 27, where should I do that? Should I do here or somewhere else? That is only the critical part. Okay,
Okay.
okay, so once you get it, then you will pop it, right?
Mm.
So once you pop it, so what is our job now? It's time for us to find okay, so it's time for us to find, right? So let's say how many nodes he has given each time. Yeah, definitely we will always get 2 nodes, so that no worries. Okay, now what is our job? We will get a current, right? So now we need to see if set dot floor of current dot value not equal to null. If it is present, it will give that. It will give that, Ajay. Understood?
Okay.
Okay. So you will get that. If it is not equal to null, then what you can do? Minimum absolute difference equal to math dot min of minimum absolute difference math dot absolute of current dot value minus, actually you don't need to apply absolute here. Floor means greater value only, na? Yes or no?
Yeah.
So minus current dot value. Okay, this
Okay.
this is one, and we can also check for seal.
Next one, which is
And
seal.
floor means next greater element. Okay,
Yeah,
next.
seal is less than one. Yeah.
Is it seal or
I think CIL it would be. Sure.
ceiling, flooring? Let me see the method names.
Yeah, right. Actually, ceiling. Correct.
Is it floor or floor? It is floor. It is ceiling.
You're right, ceiling.
So you will get ceiling, and yeah, you can have current dot value minus ceiling. Done.
Yep.
Yeah, this is
We need to go to the right, or we don't need to.
that's what we are
When you
using
travel,
travel, right? So it's not a concept of left right. If you go gone now, and you don't know which is the minimal value.
Oh, right.
Minimal difference.
This is a little tricky one. Yeah, I need to see.
Yeah, what happened? Is it not popping at all? Ah, yeah. Oh, you are talking about this one, right?
Yeah, that traversal. Yeah.
Yeah, we should do that. Ah, so actually, I should write this. Top.
Correct.
Why? Let's see. So the problem I feel here, because greater than or equal to. Okay, so what will happen next? Floor means immediate greater than or equal, it will give Ajay. Seal means
Yeah.
immediate less than or equal.
Yes.
So that's why it always being 0. The reason is we are already added those value earlier.
Correct.
So what we can do, so we will add later, so that it will solve. Understood?
Why shouldn't I didn't get that? Like, why
So
we're
what
moving
will
that one?
happen, if you see here, let's say you get into one value here, right? By the time you come here, which is already been added here, correct?
Correct.
So when you call floor, let's say you have 4 is already added here, and you got 4 here. When you call
Correct.
floor method, it will always return 4 only, even you have 5, 6 also.
Correct,
It is
yeah.
greater than, next greater than or equal.
Right. Or equals.
Here also less than or equals. So what is going to happen? So what will happen? It always be 0. That is the case, right?
No, that would be previous smaller elements, right? Not next. Line number 39.
Floor is
The floor is correct. Floor is correct. Next greater. Seal is the one.
yeah, previous. So what you should do? So if you, instead of adding here, if you add here, it will work. Understood?
Mm-hmm.
Okay, maybe floor means smaller, seal means greater, I guess. You are getting in negative value, na?
Right. I think we use floor and seal for decimal numbers. So floor is basically, yeah, lesser value. Let's see.
Seal is greater value.
Um,
We will just. Yeah, that's how it works. Of course, it's not super performance code, but it's fine. But it's a good concept, right? Vijay?
yeah.
So that's how it works. The best way is we should identify the bugs. So
Yeah.
that we can do only if you understand concept better. I think we are enough for today. We will solve them. What I felt is I have to teach all the problems because those are not direct. Everything
Okay.
has a separate concept.
Okay.
You also still give a try.
Sure.
Yeah, My plan is if we complete beginner level in each order, then we will get into intermediate level. Actually, when I was asking ChatGPT, it was giving same problem in different levels. So I just eliminated
Okay.
duplicate problems and added unique problems. It means you can solve
Mhm.
same problem in different perspectives, so that you can have better practice. Let me stop recording.